All right, everyone. I think we're going to go ahead and get started. Um, Pranit, can you advance to the next slide? So I just want to welcome everyone to our webinar. I am Ken Delaney, Industry Liaison for the FREEDM Center Center. We are the Power Electronics and Power Systems Research Center here at North Carolina State University. We have 12 faculty, over 100 graduate students, and do about $6 million a year in research funded by federal agencies, corporate sponsors, and state level projects. We have multiple labs, including our high bay, where we conduct high power testing at up to 15,000 volts. Next slide. So many of you know, but FREEDM stands for Future Renewable Electric Energy Delivery and Management. We started in 2008 as a National Science Foundation Engineering Research Center, and today we categorize our research into 4 pillars: wide bandgap power electronics, electric transportation, modern power systems, and renewable energy. Projects can bridge multiple pillars, like when we develop silicon carbide solutions for renewable energy applications. Next slide. Our industry members engage with the center in multiple ways, including leveraging research funding as project partners, early access to intellectual property, discounts on testing services in our labs, and of course, lots of interactions with our students. Today's speaker is Pranit Pawar, a FREEDM graduate student working in power electronics. Pranit received his undergraduate in electrical engineering from CRCE in Mumbai, and his work experience includes time at IIT Bombay, Ultraviolet Motors, Tesla, and Heron Power. So just as a reminder, all attendees are muted, so please ask your questions through the chat, and I'll ask Pranit as we go along. So Pranit, let's get started.
All right. Thank you so much, Ken, for this. And good morning, everyone. Thank you all for being here. I'm Pranit, and I'm working with Dr. Wensong Yu. And this webinar will be about a wide input auxiliary supply for modular SSTs. So first, we will start by highlighting the need for a solid state transformer and why do we need modularity. We'll then follow up with one of the hindrances for modularity and how at FREEDM we are solving that. We will then follow up our proposed method with validation and comparison with the state of the art. So first off, we start off by looking at the load side demand. So we can see that in the last 4 years, we have seen a lot of adoption of machine learning and artificial intelligence, particularly in the well-known forms of chat, chat GPT and DALI. And these models, they take a lot of energy so as to run. And uh, given in a report, we can see that the data center load has shot up by more than double the amount. In parallel with this, there's there has been also a very high uh, p- penetration from the renewable sector. So shown here is a graph from the Lawrence Berkeley lab study, and what it basically shows is there is about 1000 gigawatt of solar that is yet to be linked to the grid, and moreover there's also around 500 gigawatt of hybrid still in the chain. So so what I'm trying to show here is that the loads are scaling up and we need a scalable grid infrastructure to solve this. However, the current efforts to expand the grid, they are bottlenecked by one of the main challenges of 60 hertz transformer shortage. And this is mainly because of the highly customized design and the material shortage. So this is where modular solid state transformers will help us. So just to give a brief on what the solid state transformer basically looks like, we first look at how a very typical distribution grid as shown over here, and linking the consumer with the grid, a solid state transformer is shown over here. So basically, solid state transformer, i- so basically it is a transformer that is controlled by semiconductor devices, and by switching these devices faster we can shuttle uh, per cycle energy faster, which means that for a given load the size of the transformer can be much smaller, and that is the biggest plus point of a solid state transformer. Furthermore, when we modularize this and we built the whole SST from modules, as can be seen in this slide. So when the whole system is built out of multiple modules as shown at the bottom, we can then stack these modules in series and parallel so as to meet the required voltage and load demand. One key benefit of modularization i- is that this whole thing will have much lower downtime, meaning maintenance will be much faster. Furthermore, what I would like to highlight is the structure of the module it's, itself. So this module houses both high voltage and low voltage circuits. So this low voltage circuits can be the sensors, the gate drivers, the controllers. So one of the challenges then comes up: how do you supply this l- low voltage auxiliaries? So there are multiple ways of doing that, and they broadly fall under two main categories. First is this low voltage auxiliaries can be supplied by a power supply that sits r- outside the module, and this is usually powered by a 120 volt mains line. However, given that this sits beyond the module, the voltage isolation requirement is significantly higher, and that is the biggest challenge when using this kind of an external supply. Um, Now, one more strategy is to supply the low voltage auxiliaries with a power supply block that sits within the module. And when within the module, we can then derive the power for that block directly from the DC bus. The biggest plus point over here is the fact that because the block is highly localized, the highest isolation that it has to bear is just the maximum DC bus voltage. And that leads to much smaller form factor, and that also helps with modularity. So now we know that the local power supply is the way to go. We now look into what are the challenges that have to be solved for this. So shown here is a switching cell diagram, a conceptual diagram, and therein sits the local supply that derives its voltage, its power directly from the DC bus. So one thing to note here is that the maximum bus voltage for a cell can go very high, and it can reach voltage levels of 2000 volts, and that brings up the first main challenge, that is high V input voltage. Moreover, when faults happen, the bus voltage will fall down significantly, and during this falling event, the local supply has to remain functional. So that brings us to the next challenge, that is the local supply should work for a very wide voltage swing. And further challenges are associated with size, cost, component count, and the number of switching nodes. So though it looks like the local supply is a very small block, but it has to solve six challenges in one block. So how are the state of the art solving this, and what are they doing? So here we can see some six of the state of the art, and this mainly solve the challenge of high voltage operation by either stacking multiple modules in series as can be seen over here and here, or they stack multiple switches as can be seen over here and here. One thing we can a few things actually we can visibly see is that firstly, the component count is still very high, and secondly, this have multiple swing nodes as can be shown in the red dots, and we'll go over this slide in detail in a later slide. So there is still a very wide gap, wide range of challenges that still have to be solved, and that is what we have done at Freedom. So here's showing our solution at a glance. We are sticking with the simple flyback topology for its simplicity and low component count. For high input voltage operation, we are using a 3.3 kV SiC based supercascode switch, and that is then driven by our clamped gating circuit. And we'll go over this circuit in detail. But the gist is this circuit solves three challenges in one solution. Uh, Going forward, for wide voltage swing, uh, we have a variable frequency modulator that helps us to maintain the operation for a very wide voltage swing. And lastly, by using one single controller, we have decreased the component count and size significantly. So basically, we are solving the main six challenges in one solution. Going forward, we will be looking more into detail about the modulator, since this lies at the heart of the proposed method. So to understand how the modulator works, we first have to understand uh, w- what are the challenges that very wide voltage swing bring in. So we can do so by formulating the power flow. So shown on the left is a simplified schematic of the flyback, and when it is working in the DCM region, the input power can be written as half L I square times the frequency, and the power delivered at this secondary side can be formulated as the mean diode current multiplied by the V output. This can then be rearranged and represented in a circuit as shown over here. So our simplified circuit basically boils down to a load that is driven by this current source, and by controlling this diode current, we can regulate the V output. However, for a very wide V input swing, we can see that the mean diode current function is a highly nonlinear function, and that is dependent on the square of the switch current. That is first thing. Next, the switch current by itself is dependent on V input, and that in turn has a very wide swing. So the challenge is that that regulating V output for a very wide V input is quite difficult. One way to look at this is that uh, this term half Li squared represents the per cycle energy that is delivered. So when the V input swings, the per cycle energy delivered changes a lot. So that is one of the challenges that the controller has to face. Moreover, uh, the controller should also vary the number of cycles that it has to do so as to meet the load demand. So the controller has to simultaneously fulfill both of these challenges. And the way we have done in Freedom is, firstly, we have made the per cycle energy delivered as constant. So that we have done by using a fixed peak current control scheme. Uh, so by this scheme, we have changed a variable quantity shown on the left as the switch peak current to a fixed value, capital IQ peak. This then boils down the large signal model as shown over here. So now the large signal model is freed from a very big non-linearity, and now the controller just has to vary the frequency linearly so as to regulate. We then validate this large signal model by subjecting it to a step change in frequency, and what we see is the derived large signal model behavior matches well with this switching circuit. We can then go one step further and also derive the small signal model so as to get the control to output transfer function. Now, one thing to note over here is that this small signal model is free from V input quantities, and this means that the small signal model is free from any wide voltage swings, which further which further makes the whole system very robust. Now we can also represent this same model with the same circuit as shown before, and we can obtain the control to output transfer function by writing V output as the mean diode current m- multiplied by ZRC as shown over here. One thing to note is that this ZRC is a first order system, which means that when we derive GVOF, that is V naught upon F, this becomes a first order system. So what I'm trying to show here is with the given methodology, we have boiled down a highly nonlinear system down to a first order system, which can then be compensated with a simple PI regulator as shown in the green curve over here. So I spoke a lot about the modulator, and now we'll look at the actual modulator structure. So shown here is the modulator structure. It is built of comparators U1 and U2, which generate the set and the reset condition for G, which drives the flyback switch. So first we look at U2. So U2 generates the fixed peak current control feature. How it works is quite straightforward. The switch current is compared against a fixed reference, and whenever the switch current goes beyond this threshold, the switch is turned off. So what we can see here is when V input varies, the switch current would rise faster, which means that the switch would be reset much faster. And similarly, when the switch current, when the V input is lower, the switch current would fall would rise much slower. So the switch would be reset uh, after a longer time. So U2 basically controls this switch on time. And next we look at the working operation of U1, which gives the variable frequency operation. The main philosophy behind this is that by monitoring the output and by looking at how faster it dips, U1 would set the switch faster or slower. So for example, when the load goes up, the V output would fall faster, which means that U1 should switch on the switch much faster. And say similarly, when the load decreases, V output would decrease at a much slower rate, which means that U1 will set the switch, like U1 will wait for a longer time before setting the switch on. So that is how U1 gives a variable frequency operation. And to validate this in say simulation, we have subjected the model to to two key disturbances as shown over here. So in section 1, the model is subjected to a wide V input swing, and in section 2, it is subjected to a load step. So firstly, when it is subjected to a wide voltage swing, we see that the modulator maintains a fixed peak current by modulating the switch on time that is shown over here. Similarly, we can see that when the load step is given, the modulator ramps up the frequency as governed by this formula here, and it maintains the operation. Uh, Throughout this operation, we can see one more thing, that when the voltage swing is given, the frequency doesn't change. And likewise, when the load step is given, the fixed peak current doesn't change. So we can say that both the controlled quantities, that is switch on time and the frequency, these are controlled in a decoupled fashion. And that also can be seen in this graph over here. So next, we then move on to the experimental validation section. Shown on the left is the prototype of the local power supply. We can see that it measures smaller than a credit card. And to subject it to a wide voltage swing, we are using these two DC supplies that are controlled by a sinusoidal reference. This that sorry, so the local supply is then also subjected to a load, a step load, and to quantify its working, we are looking at the VGS, VDS, and the switch current. So firstly, we subject the local power supply to a wide voltage swing that can be seen over here, and we see that throughout its working, the switch current is maintained at a fixed peak value. That shows that the modulator varies the switch on time so as to maintain that fixed peak current. Next, We then give a step load. So here we see that the load is stepped from 100 to 10%. And while it does that, we see that the modulator varies the frequency. And throughout both the disturbances, we can also see that the local supply maintains its output to a stable value. So this confirms the robust wide input and variable load operation. Next, we look at the startup and shutdown behavior. So shown on the first graph over here is the V input, and we see that when the voltage goes to around 200 volts, the local power supply starts up and it maintains its functioning right until the point when the voltage fed drops to nearly 200 volts. So this confirms the startup and shutdown behavior. And now we look at the proposed clamped gating circuit. So I'll spend a few minutes over here just to explain the working of this circuit. So during the start, when both Q1 and Q2 are switched off and the voltage supplied, uh, the Zener diode DZ gets biased. So the gate of MOSFET Q2 gets clamped to a fixed voltage VZ. Next, when Q1 switches on, the VDS falls down, which means that the source of MOSFET Q2 falls down. So now we have a fixed voltage at the gate and a falling voltage at the source. So the VGS starts to goes up, and that's how MOSFET Q2 switches on. Similarly, during turn off, when Q1 VDS goes up, that is the source voltage of Q2 goes up, the VGS of Q2 starts to fall down, and that's how Q2 switches off. And to quantify this behavior, we then monitor firstly the VGS of the switch Q2, followed by the VDS of switch Q1, and for support, we also look at the gate of the Q2 MOSFET and its VDS. And here's the waveform that has been obtained. So first things first, we see that the gate of Q2 has been held at a fixed value, and when the Q1 node swings, as can be seen over here, the VGS of Q2 goes up, and when Q1 VDS goes up, Q2 VGS falls down. So this confirms the behavior of our clamped gating circuit. Now, few things I would like to mention over here is, firstly, this clamped gating mechanism fixes the maximum voltage swing that is seen by the low side switch. So when you look at the second graph, we see that the maximum voltage swing has been limited to the maximum voltage by the Zener diode. So by having this voltage sharing strategy, we we no longer need a voltage balancing mechanism. So that saves cost. Secondly, we also see that one of the swing nodes, that is gate, has been fixed to a constant value. So the clamped gating mechanism decreases one swing node in the entire solution, and we only have just one dominant swing node, that is here, and that is the lowest possible number that you can get for a flyback converter. Moving forward, we have also validated the small signal behavior, and we have done so at a corner case, that is the lowest input and highest load, and we see that we are getting a phase margin of 35 degrees, that too at a crossover frequency of 3.5 kilohertz, which indicates a good stable response. So now we look at how does our proposed method, proposed local power supply fare with the state of the art. So when you look at the state of the art, which utilize module stacking strategy, as can be seen in this and this, one thing that we can visibly see is the number of swing nodes. So these methodologies have multiple swing nodes that have very high voltage swing. Furthermore, we can also see that these solutions have high component count, and this drawback can also be seen in the single transformer stacked switch uh, strategies. These solutions have multiple swing nodes with a voltage swing of at least half the DC bus, and moreover still the challenges of component count have still not been solved, and that leads to cost increments, and that can be visibly seen in this curve, this bar graph. So W2 and W3, which utilize the module stacking methodology, they have multiple transformers, and that is what drives their cost up, that can, as can be seen in the green bars. Whereas on the other hand, W1, 5 and 6, which utilize multiple stacking of switches, uh, they need voltage balancing circuits because they have multiple switch in series. So a majority of their cost comes from the voltage balancing circuits, and that can be seen on the dark blue bars. With the proposed methodology, since we have eliminated the need for a voltage balancing circuit, we are doing away with this cost completely. Moreover, the gating mechanism that we have used, that is developed with less than 40 volt rated components, which cost significantly lower. Uh, the only major cost that we see for our case is from the 3.3 kV SiC MOSFET, and that is again uh, expected to drop as the market matures. Finally, for our next steps, we have validated the local power supply behavior on a system level. So shown here is the front end of the modules. So basically what we want to see here is how does the local power supply behave whenever there's a fault. So so we have generated a fault with the breaker as shown over here, and whenever fault happens, the bus voltage starts to fall down. And whenever the bus voltage falls down, uh, throughout the whole duration, we see that the local supply maintains a fixed output voltage. And similarly, when the fault is recovered and when the DC bus voltage starts to ramp up, The supply is the first one that gets powered on. And we are now validating this in a fast charger that we are developing at Freedom. And here I'm showing the three modules of those. Finally, we have filed a disclosure for this work that we have done. We are at a technology readiness level of 4. For further details regarding this work, you can refer to our uh, published journal paper. And for more details regarding the commercialization, please contact Ken. And with that, I'll take any questions, any suggestion, comments.
Thank you, Pranit.
Thank you, Ken.
We I did share a reminder that if you have questions, put those in the chat. Give everybody a second because that was quite a bit of information
Yeah.
to share.
Well, I can go back on slides if needed, and I have some backup slides as well if further data is needed. So just shoot a message and I'll go right there.
Okay, certainly. And actually, probably go back one slide just in case people want to
Yeah.
view the QR code.
Yeah. Sorry.
Keep going back. You can get rid of my picture. But it's no, that's fine. I mean, if anybody does have questions, they can certainly
Yeah.
contact me, and I can relay those to Pranit. But there is a lot of information. Many of the things that you've seen are in the IEEE paper, and Pranit, you're going to present this at ECCE as well.
So we did this last year.
That's right.
Yeah.
Okay.
Yeah, we do have demos in our lab. So
Okay, and you did this at APEC or ECCE last year?
ECCE.
Okay. Okay. Yeah. So if anybody online that has other questions, you can also go back to some of those conference papers um, to review anything. All right. So can you see in the chat, Kenny has a question?
Mm-hmm. So
Um,
Kenny says, since this is a general topic and it's a developing one, where do you first see SSTs being used in real world projects? So I would go back to slide 1, and that should clear a lot of things. Oops, this is a lot of data. So the first sector which I feel this would benefit from is the solar, because there is a lot of solar energy that is yet to be linked with the grid. Second sector which I feel is the data center application. Data center is a huge market, so right now it is valued at around $1 trillion. So these hungry data centers, the loss that they generate is significantly high, and given the boom of artificial intelligence models, the power consumption is only going to rise up. So, so in short, solar and data center application.
and Pranit, you mentioned that the actual application for your prototype is in fast charger
Yes.
application, which
Yes.
again, there are commercially available 1 megawatt DC fast chargers for think, electric school buses or large trucks or
Right.
single SSTs that may be feeding multiple charging stations at 100 kilowatts or 200 kilowatts, whatever the rating may be.
Right.
But one of the benefits of using the modular approach from a solid state transformer is that the traditional design, and Pranic, correct me if I'm wrong on this, but the traditional design is you have a grid frequency transformer that brings in the medium voltage, typically steps that down to something like 480, which is then distributed to multiple charging dispensers, right? That
That's
may
correct.
do then the AC to DC conversion at those dispensers.
No. Right.
And the design that we have, you actually can remove that low frequency transformer, which is one of the key sources of bottlenecks
Yes.
in electric vehicle deployment and in data center development. It's just that the generally due to other the supply chain constraints, those grid frequency transformers are in short supply. So we can go directly from medium voltage at the grid level, 13.2 or up to 15 kV, through a solid state transformer directly to a DC bus that then may distribute it to multiple or single dispensers. And so
Yes.
that has several advantages from a smaller footprint standpoint. You don't have the expensive in short supply grid frequency transformer as well. So that may be another application where you may have constrained space, but
Yes.
still need high power applications. So
That's
that's
correct.
yeah, one area that from discussions I've had with utilities and other industry members that would be a potential application as well.
That's correct. Yes.
So can you let us know if that answered your question? Hopefully it did. And does anybody else have questions? Okay. Well, if you do, my contact information is there. And we thank everybody for joining. Just to let you know, this is part of our renewed technical webinar series. So we are planning others in the future, and we'll let everybody know when we plan to offer those. All right. Thank you, everyone. Hope you enjoy the rest of your day.
Thank you, everyone. Goodbye.